All right, everybody. I am going to talk a little bit about biomechanics. Don't be too scared. Hopefully it won't be too mathematically heavy or anything for you. I didn't actually come up with the title for this. While it's, oops, wrong button. While it does say for age group swimming, a lot of biomechanics, really, it just has to be applied through all levels of swimming, not just age group stuff. So we'll talk through a few kind of basic principles and how we apply some of those to actual swimming stroke technique, as well as touch a little bit on starts and turns. And I'll try to leave a bit of time at the end in case anybody does have any questions. First, I just wanted to clarify a few things. Biomechanics is not race analysis, okay? For various historical reasons, which I don't really need to get into, especially here in Australia, this is what everybody, when you say biomechanics, that's the first thing people talk about is what's the race analysis that you just did at Nationals, whether it's Green Eye, Sparta, whatever. That's not really what it is. It's kind of, race analysis is a means to an end, and it really should live with the performance analysis groups, which are a totally different thing. But we end up using the data that comes out of race analysis to help guide any kind of interventions that we may look to do in a daily training environment. It is also not just standing around holding a camera for you to collect a bit of footage that you can look at later. Okay? If you want somebody to do that, go down to your local high school, get a student, and have them stand there with the iPad. We're really strapped for real biomechanics support in Australia. So if you do just need a bit of footage taken, you can do it yourself, or find a student, assistant coach, athlete that's out injured, anything. Okay? You don't necessarily need to have that. We obviously use video a lot for biomechanics, but that's definitely not our primary role. So if you can just kind of take that into consideration when you are looking for, if you do need biomechanics support, that's fantastic, but think about what you actually need before you ask for it. It's also not really, we're not a technical coach, okay? Biomechanists are scientists, okay? We may have, like I've, obviously got quite a long history with swimming, so, in theory, sure, I could fill that role, but we are not a replacement for the coach. We are advisors. We'll give you recommendations based on the physics and the science of swimming, but we're not a technical coach, okay? And again, sometimes that line gets blurred, and it's not always the coach's fault. Often it can be the biomechanist's fault. They can get some delusions of grandeur. But again, we just gotta kind of lay that framework so we don't cross those boundaries. So what it is actually a science. It's based on physics. And it's our main reason for study is to work out what the forces are in any kind of, for sport biomechanics, what all the forces are that are acting on that athlete, and what techniques are they going to then use to maximize those forces or reduce some other forces. So that's the whole thing that we do. And we are a resource, okay? And we should be making recommendations based on the physics of the situation, not on the latest coaching theory that gets shot around on Swimming World or whatever, all right? When a biomechanist gives a recommendation, almost the first question you should ask if you get a recommendation for them, what's the basis for that recommendation? And they should be able to tell you. Often, like if I'm doing feedback, I may or I may not necessarily get right into it on why I'm making a suggestion, but if you ask me why I'm making that suggestion, I'll always tell you, and I'll base it on the physics of the situation, okay? If I'm gonna make an adjustment to the angle of somebody's arm on a catch, I'm gonna tell you why, that I'm trying to reorient the angle of that force application, things like that. One of the problems with swimming is that we find it really, really hard to get any real measurements out in the middle of the pool. That's why we do a lot of start and turn analysis, because we can actually measure things. Okay, so a lot of the techniques that we would use on any kind of land-based sport, we don't really use in swimming just because it doesn't work. So this is where you kind of get a lot of the stuff that we would do on land-based is going to be based on research, actual measurement that we can take. Whereas with swimming, we kind of have to use more of the educated, not educated guesses, although it is to some extent that, but educated use of the physics. So we really need, and I tell my students that all the time, even the ones that know nothing about swimming, it's just think about it logically. What's the aim of the skill you're trying to do? Where the forces need to be applied? How are we going to adjust a body position to get those forces to act the way that we want them to? Okay? So that just kind of hopefully clarifies what we're talking about. Just a few things I want to go through just to kind of lay a bit of a framework. So when we are talking about biomechanics here, or if you're talking with a biomechanist at home, there's a few just terminology things we just need to kind of lay down for you. So when we do talk about references within the body, we talk about these planes of motion, movement, whatever. So they are, because we move in a three-dimensional world, we've got 3 planes and 3 axes. So transverse is that kind of cuts you in half plane, so anything that happens in there. Frontal plane cuts through just like you're looking at somebody head on. And sagittal plane, if I'm standing side on, anything moving, kind of cutting me down the middle. Sorry. And then we have so that's actually for motion, straight line motion, or you can have rotations in those planes. But then the axes of rotation, and this is where you start talking, like if, we've got freestyle and backstroke, we call long axis strokes, butterfly breaststroke, short axis strokes. That's where that comes from. So you've got the anterior posterior, so that's just the one that kind of comes right through imagine spearing you through the navel. Longitudinal, so that's our long axis, so that's the freestyle backstroke rotation about that axis. And then the medial lateral going side to side, so that's the hip flexion extension. So that's where we get the butterfly breaststroke, short axis strokes. All right. A few other terms, force. We don't need to get into energetics and everything like that, but basically a force is something that causes motion in a straight line. Okay? Pretty simple. A torque is something similar, but it causes a rotation about an axis. So there is a slight difference in that, straight line and rotation. Swimming is, or any kind of aquatic-based sport, like normally for land-based sports, we don't worry about center of buoyancy. But we do, for everything, we deal with center of gravity. Center of gravity, center of mass, whatever you want to call it, it's the same thing. So essentially what that is a single point in your body that represents all the mass of your body, all right? If anybody ever done the trick how to find a center of mass on a stick or anything? You start wide and you kind of slide your fingers close together. So it's basically that kind of balance point, right? That's exactly what that is. So if I were to lie down on the ground here, my center of mass is going to be roughly there. If I raise an arm up that way, I've got more mass on this side, so it's going to shift up slightly. More mass this way. It's going to keep going up, depending how you move it. So it's not a fixed point. It is going to move according to what position your body's in. Center of buoyancy is slightly different in that it's the center of the mass of the displaced water, okay? So if you think about when you're lying in the water, you and the water don't take up the same space at the same time. You're displacing that out. So, and not all of your body is necessarily going to be underwater. So if you're lying like this, so you got to lift back your head, bottom's sitting out of the water. So really, we're only worried about this bit that's under the water there. So it's going to be the center of that volume, which again will change depending on how you're positioned, how much is up out of the water. Okay? We'll talk a little bit more about that in a second. Another term that you will run into every now and then is impulse. And what that is gives you an idea of roughly how effective a force is going to be when you apply it. And how you get it is you take this force that you're applying and how long that force has been applied for. So really, we're looking at the area under the curve. So in this case, you can apply a big force over a pretty short period of time, or you can apply a lower force over a longer period of time. So you could apply this to stroke rates, all those kinds of things. So it's a useful thing to know that there are, basically there's more than one way to skin a cat in a lot of ways. That you need to have an output of a change in velocity. So that's what we're trying to achieve, right? And you're going to do that by applying a force over a given period of time. So you can either do that with a really big force all at once, or a lower force over a period of time. Another one is velocity and acceleration. Sometimes this gets a little bit muddled for some people. It's not, in theory, it's not that complicated, but it can get a little bit confusing at times when you start talking on deck and things. So really, the whole way this works is as you move, you're going to move through some given distance, right? How far you move in a certain amount of time gives you that velocity, okay? So if you're changing that distance consistently, so you're just kind of moving, I'm moving in a consistent velocity, so your velocity is flat, right? But if that starts to change, if the velocity that you're moving in starts to change, that's where we have accelerations. So you either, as you're speeding up, it's a positive acceleration, slowing down is a negative acceleration, all right? So you see that obviously as you look at any swimming stroke, we run into these all the time. So the influence of that, again, we'll talk about in a little bit. But so basically, velocity is the change in distance in a given amount of time, and acceleration is the change in velocity in a given amount of time. Okay, makes sense? Hopefully, sort of. All right, so you really can't talk about any kind of physics really without talking about Newton's laws. So these are basically three laws that more or less kind of govern physics as we know them, really, at least the kind of physics we're talking about for this. So this is kind of the main one, a body in motion or body at rest will tend to stay that way unless the force acts on the body. Okay, that's the old, you're floating in space, moving along. There's no other forces acting on you. How do you stop? How do you change direction? That's why you always keep the spare wrench. Remember that if you're in space. You throw it away from where you want to go. And you get a reaction because you get another force. Otherwise, you'll just keep going in one direction forever. So we obviously don't have that problem. We've got forces acting on us all the time. So we don't tend to just kind of keep moving. This is the old, before Einstein came up with E equals mc squared, that was the equation everybody knew. It's kind of not as common these days, it seems like. But how quick, or what the acceleration of any object is going to be proportional to the mass of it, how big it is, how massive it is, and the magnitude of the forces that you're actually applying. So if you have a light object and you apply a big force, you're going to get a high acceleration. If it's a really massive object, same force, you're going to get a low acceleration. And then you can play around with all the different combinations. And then everybody kind of knows this one for reaction is an equal and opposite reaction. So those three just kind of frame everything that we're going to be talking about. All right, so to apply some of these to actual swimming, when we do talk about stability with relation to buoyancy, when you become stable when you're in the water, what needs to be happening is that if you draw a vertical line through the center of gravity and a vertical line through the center of buoyancy, they basically need to be lined up. So if those two are lined up, then you're going to be stable. If they're offset, like they are here, okay, you're actually going to get a rotation, because things are going to tend to rotate basically around your center of gravity, your center of mass. So you can just imagine that center of buoyancy is applying a force to the body, and it's trying to rotate your body around the center of gravity. So it'll keep pushing you up, really, until the center of gravity lines up underneath you. So again, you can change that though. That's why you get, lie out, long streamline. What's happening to the center of mass? Okay, like I said before, if you're like lying in the water like this, legs are going to tend to sink. The center of mass is here, and the center of buoyancy is here. Okay, if I do a nice long stretch, I'm going to shift my center of mass up. Center of buoyancy isn't really going to change too much because you have the same submerged volume. It'll change slightly, but not too much. But they'll be in more closer position where they're going to be lined up, so then you can float level. Okay, so you obviously need some strength and things as well, but that's the main criteria for being stable in the water using buoyancy. Okay, another thing we have to take into consideration, and this is for most complex movements, not just swimming, but how many joints are involved in joint sequencing. So this is when we look at timing through, going from catch, in sweep, out sweep, whatever. How we actually sequence that motion is actually really important. It's how, when you if you're throwing a ball, you're not going to go there, stop, throw there, or you're not going to go there and do some random action. It's going to be one big sequence, usually starting at the big body parts. So with your trunk, moving through the upper arm, forearm, hand, to get the biggest cumulative effect, in this case in velocity. So if you time things properly, and that's what we'll see when somebody times how they initiate a pull, you'll get that proper sequence and you'll get an optimal outcome from the hand speed. Okay, then like we were saying before, talking about impulse. So this here is roughly a hand force curve from a freestyle pull. So this is entry, just early extension leading into the catch. And then once the hand actually starts moving backwards, you start actually being able to apply a force. You can see it as the hand is accelerating through the stroke. You'll get an increase of force to a point, and then it drops off towards the finish. So that force there, for swimming purposes, we would call a resistive or a negative force, because you're moving against the flow of water, so you're actually essentially slowing yourself down. And then all the green is the positive, more propulsive forces. Okay, and then the direction of the force. This is where you get into the debate on lift and drag forces. Everybody somewhat know about contribution of lift and drag to propulsion. You guys done a bit of that? That's been a discussion that's gone on for 40 plus years, really. Probably actually quite a bit longer than that. And again, and this comes back to the earlier statement where we find it really hard to actually get some of these measures. So there's been a little bit of research on this, but it's still not 100% for sure. We still don't know precisely what the contributions are between drag and lift to get most out of propulsion. It has changed quite a lot. In the old days, everything was pure drag, so it was just everything straight line, kind of paddle wheel motions. You just wanted to apply everything straight back. Then you had councilmen in the 60s saying, no, it's all lift. And then that changed again back in late 90s, early 2000s, I suppose. And people said, no, it's more all drag. And I think really what we've seen in most of the research nowadays is that it's both, really. Probably is dominated by drag force, but there is still definitely a lift contribution. So I know it's probably just getting more confusing than anything, but we do need to kind of take that into consideration when we start looking at how forces and the direction, how forces are generated and the direction that they're actually being applied in. And just don't forget that there is going to be some kind of lift contribution to what's happening. All right, now the biggies that we do have to deal with And so this is just the fundamentals of it. So again, when you're talking with the biomechanist, they should be thinking, because the aim of swimming obviously is to get between point A and point B as fast as you can. So the way you do that is you increase propulsion and you reduce drag. So the first thing we've got to do is try to reduce drag, hopefully. So just so we're clear, there are 3 main types that we're dealing with. There are a couple other small ones, but they don't have much effect on swimming. But for our purposes, the big one and probably the main one is form drag, which is really your frontal area. So how much, if you're looking at me head on through the water and you can see that much of my body, that's quite a big frontal area. If I get down into a streamlined position and you look head on, it's whatever area you can see. So that's one of the main influences, because really what's happening, which actually I'll show you that in a second. Second one is friction. So just the simple resistance of water moving against your skin or togs or whatever you happen to be wearing, caps, goggles, everything like that. That one does have an effect. It's not huge, okay? It often can be a bit overstated at times, for swimming at least, especially when you take into consideration what's happening with the water itself. And then we've got wave drag. This kind of traditionally has been a little bit underestimated. I'm a little bit biased on that because I did my PhD on wave drag. But it's been shown that can be up to about half of the total drag that you're encountering during swimming. Okay, so it's a big influence. And the reason how it actually works is that as you move through the water's got to get out of the way, right? So if the water gets pushed up by you, it's got to come back down again due to gravity, right? So you end up getting a wave. So to raise that water, we've got to use energy to actually lift that water up above the surface level. So that's energy that you can't use for propulsion. Okay, so it's basically a waste, which is basically what drag is. So the bigger the waves are, the more wave drag you're going to have. There's some debate that you can recapture some of that energy, but some of that's a little bit idealistic and really applies to like dolphins and not so much to humans. But the other one, so one of the things we can do is slight changes in technique. Potentially we can change something about the shape of the body. So that could be one of the things with the super suits and even some of the current suits that are really highly compressive that may have a slight effect on wave drag. Theoretically it may. Or we can play around with underwater aspects. Where wave drag is actually the highest is when you are just below the surface of the water, okay? So that's where if you've got swimmers that are coming up on a breakout and they come up and they sit 10 centimeters below the surface of the water, kicking madly and then break out, they're wasting an enormous amount of energy because drag is going to be huge at that point. So you need to be a bit more aggressive on coming through that top layer of water. What we've seen is that its maximum is kind of the top half meter, roughly, okay? So if you're coming and just sitting below that surface in that kind of depth, you are actually wasting a fair bit of energy. So how we deal with that, form drag, as I said, is really dealt with by body shape, and one of the big issues with that is length. That's what we have seen for most of the strokes. Freestyle and backstroke probably in particular, the long axis strokes, is that the athletes are getting notionally a bit taller. That probably is slowing down a little bit now, but you still look at elite level and they'll tend to be longer. Again, we don't need to get into the whole physics of that. It does relate to wave drag as well, but I'm not going to worry about that now. Cross-sectional area. For the friction stuff, what the materials are, whether you shave down, all those kinds of issues. And then there's fluid characteristics, and for these, there's not a whole lot we can do about it. The density of the pool water is not going to change. velocity, obviously that is up to us as swimmers. And then how much turbulence is in the water. And most of the time for us, that's really not too much of a problem. So the ways that we try to deal with this, the number one thing really is streamlining, and that depends on body position. And this is where we get to the thing, especially with the younger kids, that's the number one issue you should be looking at, is just general body position in the water. Don't worry about, are they getting a really nice high elbow catch, or what's their ankle flexibility like for their kick and all that kind of stuff. Get their body positions sorted out early so that we want them moving through the water like that, not like that, okay? So this kind of just while I'm here. When I do talk about form drag, this gives you a kind of a good example of what's actually happening with form drag. Because really what it is the pressure difference between the bit of water in front of the body and behind the body. So in this situation where you've got all this turbulent water through here, that's really low pressure, and you've got high pressure up at the front. So when that difference front to back is really high, you've got a high form drag. So the more you can reduce this area of low pressure behind the body, the lower the drag's going to be. That's why that position is better. You've just got a small area of turbulence. This is a bit idealized, but relative to the front. So the streamlined position like that, you're going to have a lower drag. We could, in theory, play around with some fairings like they do on aerodynamics, but that's probably not going to be allowed, I would imagine, by FINA. Another one is the surface characteristics of the suits in particular. This goes back to the old original fast skin suits. So they were saying that they were basing it on this. So that's actual shark skin. That's what it looks like. And this is what the material of a fast skin actually looks like. Not really a whole lot similar there. So they really probably were not doing what they thought they were doing, which is not too surprising for some companies. They've got good theories that in theory may work, but actually applying those would get a little bit tricky. Other ideas that companies have come up with are these things like tripwires. I don't know if you guys remember these suits. You do see them every now and then. But they had these raised loops along the body, and they had another one around the top edge of the cap. The idea behind that is the same kind of a thing as a golf ball. All right? That's why golf balls have dimples, in case you didn't know. What happens if you have a perfectly smooth ball, like in this, you can see the water tends to pull away from the surface of the ball, kind of right at the top and the bottom, right? So you get that big area of low pressure behind, so there's a lot of drag. What happens if you put dimples into the ball, like on a golf ball, or in this case you have this tripwire thing along the front edge, is, again, it gets a little bit complicated and somewhat counterintuitive, but what happens is you actually create a little bit of turbulence in that flow right along the surface, okay? The result of that is that the water actually stays in contact with the object for longer. So you can see through here. So with nothing, it separates there. When you have the tripwire, or if you have dimples, it's going to separate back here. So that area of low pressure is a lot lower. So the form drag is lower. So that's why you can play around with all these kinds of things, some of which work and some are not so crash hot. This one actually proved to be not so crash hot. Wave drag is a tricky one. There's not too many ways we can really deal with it. I mentioned potentially body shape. That's why if you've ever seen these big tankers with the big nose things sticking out the front, that's what that's for, is to reduce wave drag. They're kind of creating a second wave system out in front of the hull of the boat, which can cancel out the main wave that's being created by the bow through here. So again, it gets a bit complicated, but there are ways to deal with it. But for us, really, we're looking at depth is going to be the big one. So this is where I was talking before, where area right through here. So that red line there is roughly the amount of drag, okay? So you can see if in this case, it's talking about thicknesses. So if you go like a chest depth, okay? So if you're half a chest depth below the surface, or essentially just submerged, that's where drag's maximum. And then you need to get down to almost 3 kind of body thicknesses until you get away from that. So this has a pretty big influence on underwater kicking trajectories. The big rider, and that's why I have the little asterisk there, is based on the skill of the athlete and how good they are underwater, all right? If you have an athlete that's not that good a kicker, or they can kind of just barely kick as fast as they can swim, it's probably not worth it having them stay down for that long. You know, obviously you want to come off the wall and get through that initial bit of turbulence and whatnot, but to stay down, if they're not actually a good kicker, is pretty much going to be a waste of time, okay? And largely because it's wasting energy to move slower than you could be if you were on the surface. There's a bit of optimization on that, but as a general rule, that's the case. So in case I didn't push that before, body position is our #1 thing. So that's really where you need to be focusing as much as possible. Because if you get into a position like that, better streamline, reducing that area of turbulent water behind so you get lower drag. So everything else being the same, legs down, you're going to have a big area back here, more frontal area exposed, so you're going to get that higher drag. So really, really push that body position. Propulsion on the other side is basically just kind of the reverse. Like I told Damon, you can't have any kind of biomechanics talk without an equation. Basically, that's just, I'm just kind of being a bit of a dick, really. But essentially, that just kind of shows you how it actually works. So you do have, there's a drag component, and this is where it can get quite confusing when you read some of this stuff. You're talking about a propulsive force that's got a drag component and a lift component, okay? What it really should probably be, and then you have drag force in general. But what we should probably, when we're talking about propulsion, we probably should call that, I don't know, front to back or something, that just to kind of differentiate it a little bit. Because really, that drag component, which is defined by that, and that's actually, may look kind of scary, but it's not that bad really. So just so you know, in case, because you will probably run across that equation somewhere in reading something about swimming propulsion. So half is pretty self-explanatory. That guy there, rho, is the density of the water, which again is just, it's a constant based on what the temperature of the water is, so that's pretty stable. V is just the velocity squared. So that can be, depending what you're looking at. So that can be, if you're looking at propulsive force at the hand, that's going to be what's the velocity of the hand. If it's whole body kind of propulsion, what total propulsion you're generating, it's going to be the velocity of the center of mass. A is the cross-sectional area we were talking about before. And then that CD is the coefficient of drag, okay, which is just another constant that you work out for a given position, largely for, in this case, for the hand. And then basically the equation is exactly the same for lift, which again is just, so if I'm pulling that way, so I'm pushing on, if I pull straight back, that's just total drag force, right? All the force is kind of front to back, right? If I start pitching my hand and coming in on angles, there's actually a component of that force that's going side to side, that's lift, okay? So you got front to back and side to side, that's drag and lift, okay? So that's the only difference really in those equations is just those different coefficients for lift, okay? So don't get too freaked out by when you do see those equations. They're pretty, relatively speaking, somewhat simple. So what we do look for though is that to hold a constant velocity, that real drag force needs to be equal to the propulsive force that you generate. And when those are balanced, then you're going to have a constant velocity. As soon as the drag force is higher than that propulsive force, you slow down, and propulsive force higher than drag, you're going to speed up. So we hit those points all the way through a stroke, right? So your velocity is changing all the time, which isn't actually all that efficient. So this is the reason things aren't that efficient. Okay, remember, so Newton's second law is the acceleration is proportional to the force and the mass, right? So if you are accelerating, so that's either positively going faster or negatively slowing down, there's got to be an additional force applied. Okay, so if you're swimming through your stroke and you've got big swings in your velocity, okay, this is more of a concern as you're speeding back up. So if you have a big drop off, so even say in breaststroke, right, where that, if you look at velocity in the kind of the right in the middle of the recovery, that velocity doesn't hit zero, but it can get pretty bloody close. So to maintain that, to get back to that average swimming speed, we have to accelerate. Okay, how do we accelerate? You apply an extra force. So then you've got to accelerate to get back up. So the bigger that drop off in velocity is, you've still got a constrained amount of time. So you've still got to get yourself from that slow velocity up to your free swim velocity. So if that's a big change, your acceleration's got to be higher, you've got to have a bigger force. So if that's in freestyle, any of the strokes. So the tighter you can keep that peak to trough within a stroke cycle, you're actually going to be more efficient because things are going to stay in balance, and you'll only have to be doing just the force, relatively, to overcome drag, and you're not going to have to be doing that extra force that you need to accelerate yourself over and above what you already did. Does that make sense? Hopefully. Because it's actually pretty important, and that's why one of the things we're working on ways to get at this a bit more effectively is what is that actual fluctuation in speed throughout a stroke. Because you do see more skilled athletes, that fluctuation from fastest to slowest within a stroke cycle is going to be a whole lot tighter, much more, in all the strokes. Oops. Then, so for the third law, it's action-reaction. So for the action-reaction thing is actually, a lot of people have a lot of problems with this, conceptually. The fundamental thing, so if you look at it from this point of view, I'm standing here, so I'm pretty much pushing down on, pretend I'm on the ground. So I'm pushing on the ground, so that's my action, right? The reaction for that is the earth is pushing back up on me, okay? That's actually the force we're worried about. Not so much the force I'm pushing down, but what am I getting back? If that force wasn't coming back onto me, I would just collapse, right? So same kind of thing when we start talking at propulsion. We're not really worried about what's the force that we're applying, really. We're worried about what's the reaction force that we get back from the water. So when we start looking at, say, with kick in this situation, when you get into there, so on the downbeat of the kick with good ankle flexibility, actually pushing back on the water. So what's going to be the reaction to that? Water pushing back on the athlete. So that's when you get a good propulsive kick. You get that situation, the kind of typical triathlete kick, where if you've never seen them go backwards, they do. It does happen. And a lot of it is, it's ankle flexibility and body position in general, but they'll actually, when they kind of hook that downbeat, the force they're applying is actually, their applied force is moving towards the head, so the reaction force to that is going the other way. So it's actually tending to slow them down, which is why they tend to move backwards, okay? It's entertaining if you ever see it. But. All right, so we do have a few things that we try to use to maximize some of this propulsion in particular, and a lot of it is going to rely around the catch, so that you are able to maximize the force, you're going to maximize the mass of water that you're in contact with, that you're trying to accelerate to get a reaction force, okay? So again, if I haven't hit that enough, good body alignment is always going to help. Because remember, the human body is not designed to swim, okay? Particularly the shoulders. They're really, shoulders are really designed to exert force from here down, okay? When we're up here, the shoulder's designed to reach. That's what it's there for, okay? Not designed to generate force. So we've got to have good alignment or optimize our alignment so that we can get good force production without causing injury, okay? So that's where that kind of comes in. So we want good alignment, we want a good streamline extension, again, keeping good body length. Remember, that helps with drag reduction as well. Initiating from the shoulder, not the wrist. This is, again, remember we talked about the sequencing. When you're trying to maximize velocity at an endpoint out here, you're going to start with the trunk through the shoulder, upper arm. So that's where the anchor has got to happen up here, not at the wrist first. Ideally, this high elbow orientation, again, I'll talk about that. So, talking about the high elbow catch, which is kind of the standard, has been for quite a while. And then maintaining connection through timing and then core strength. So this is where you want to have that, again, having that good strong base that you can work off of. And symmetrical. This is another biggie, largely across all sports or across all strokes. But we want to try to be as even side to side as we can. Fundamentally, that comes back to that constant velocity idea. Okay? If you have one side that's stronger than the other, you're going to tend to have a big speed up, slow down within your stroke that's bigger than it could be if you were more balanced. All right, so you want to make sure the actions that you're doing are symmetrical so that the forces are the same, so the accelerations are the same, and you got a better shot at maintaining closer to a consistent velocity. And then you got width of the catch. Actually, I'll talk about that in a second. So when we talk about the high elbow kind of a catch, so that's your kind of classical kind of position there as opposed to that. I think in some ways this can get pushed almost a little bit too hard at times. Remember, we're not designed for force up here, right? We're also really not designed. So essentially when you get in that position, to get a high elbow, you have to what's called internally rotate your shoulder, right? So you're going to be essentially rolling your thumb in to get the elbow up. And then, I don't know if you guys have done abduction, adduction. You done all that kind of stuff? Anyway, if you're trying to move your arm away from the center line of your body, that's called abduction, okay? And if you're adding your arm to the body, adding to the mass, that's adduction, okay? Little kinesiology question for you. So our shoulders are not designed to do abduction, abduction, and internal rotation, which is what we're asking you to do when you do a high elbow catch. So people that are really good at having a serious high elbow catch, you look at Hackett's, Thorpe, those kind of guys, and you see them and they'll go out into extension through here, and then they do that, okay? The amount of people that can actually do that effectively is very, very, very small. So trying to get, especially younger kids, to do that, you're asking for shoulder problems, okay? Because what happens, if the shoulder's not structured, and you almost can't change this because it's structural issues within the joint. So those guys can get away with it. That's just the way they're built. So that's genetics for you. But what we want to try to do with the younger kids is get them to at least go towards this. So the way I usually describe it is when you're looking right around that catch position, draw a line between the shoulder and the wrist, okay? And the elbow should be at least on that line or slightly above it, okay? If it's below the line, that's more of a problem. And because when you're talking that or that, you're still okay. You're not going to be doing much damage. But you look at the difference in position that can then entail particularly with the hand. You know how we're talking about the direction forces are applied. You get the high elbow, you're going to start getting the hand into an orientation where it's going to pull back on the water. drop the elbow, the hand tends to flick up, and you're actually pushing just like the triathlete kicking, okay? Pushing it the other way against the water. The other advantage too, remember one of the big things that when we talk about force application is that surface area. Remember the little equation, cross-sectional area? So when you start getting that high elbow, you actually start utilizing the forearm a bit more. How much of the forearm we're actually using is debatable as well. In theory, once you get into the main part of the in-sweep in particular, you will actually start using some of the upper arm, but again, we don't really know the exact contributions of that. So fundamentally, try to get them close to that, and you can think about that with the other strokes too. Those kinds of, anytime you're calling for a high elbow position, just try to think about that orientation, and remember we got to try to look after shoulders. If they can do it, as they get a bit stronger, as they're developing, and you see that they can do that, no problems, that's great, good for them. But don't try to make every kid doing a Hackett, because you're just going to trash them. Again, for the kick, similar kinds of things. So you'll see it's basically almost the same as with the catch. Good body alignment, initiated from up here, from the bigger segments, not down from the knees or the ankles. Flexible ankles are obviously a benefit, like we saw in that kick slide before. If you have good flexible ankles, you can get the top of the foot pushing back on the water without a lot of knee bend. So again, you're pushing back without sacrificing extra drag from dropping the knees down to get that position. And then again, the timing, and again, symmetrical, okay? A lot of this stuff too, it's really just kind of reiterating the big issues. So for flutter kick, obviously the ankles are a big thing. You can improve that a bit, so it is worth working on kids with ankle flex, getting their ankle flexibility better. It is a hard one to change, but it can be, every little bit can be beneficial. So the consequence, like I just said before, if you do have poor flexibilities, you end up, so if they can't, let me see if these shoes on, I can't do anything, but so assume my foot was pointing back. So if I had good pointed toes, I could be like that. But if I don't have good ankle flexibility, and I'm only like that, I got to do that, roughly, to actually get that foot into a good position to kick. So that's why if you don't have it, you're going to get that knee bend, and that's going to cascade. Your hips are going to drop down. Everything just kind of turns into more of a cycling motion. And that's a big one too, between both of these types of kicking. It's got to be at two directions. Okay, it's way too often that we see everybody's really good, strong downbeat kick, but then just kind of floating back up or little flicks and things like that. You obviously have to modulate that a bit depending on the distance that you're going. 1,500 guys are not going to be doing the massive upbeats, but especially when you start talking the sprints, it's really got to be two-way. And it, not only for flutter, but especially for dolphin. Because there's a lot of power that you can use, especially for dolphin, just because of the way the movement works. You start utilizing some quite big muscles through your core. So it really, rather, if you see the kids that are dolphining just from the hip, it should be starting up here, just below the chest. Okay, that's kind of your main base hinge in a dolphin kick. So one thing you can look for that they're not being kind of symmetrical is if you watch the kick and at the end of the downbeat, their hips kind of pop up, okay? That's a sign that they're not initiating that back upbeat effectively. So if you watch somebody, because if you do a downbeat, really to get power out of it, you've actually got to start that return to get a whip on the end. So if you're not initiating that return early, you get that, and then they'll do this. So rather than down, I did that wrong. So you're starting the return, just take my word for it, because I can't do it while I'm standing on that thing. But so that is a good little sign. Just look for any kind of real big pops in the hips. It should be a nice continuous motion. So those are just some more examples of things, what we were talking about. So you get that kind of more sprint type technique there. A little bit straighter. That's actually the shocker we want to avoid at all costs. That's another tricky one too. That's starting to get a bit too close. The problem with that is, remember that we have a big influence on the water around the body, okay? So you're actually playing with water flow all around you. So if you start pushing with your hand into here, you're actually gonna start pushing against water that's already been made a bit turbulent. So it's already got some motion into it. So when you apply a force, you're not gonna get as big a reaction from it. So having that bit of extra depth, you get into roughly more still water, so you can actually get a bigger reaction force from it. Obviously the problem is, the further away from that you get, you put more load on the shoulder. So that's why we kind of try to optimize that a little bit. So putting that, classically around 90 to 100 degree angle through there, maybe a little bit bigger if you're sprinting, and a little bit closer probably if you're distance. When we start looking, so that's kind of the Hackett thing I was talking about before. If you can do that, good on you. But again, with the younger kids, don't shoot for that too early, because it can do more damage than good. The other thing is pull width, and that's where we get into more of the torque thing. Remember we were talking about when you apply to balance with center of mass and center of buoyancy, when everything kind of aligns, because you get a torque from the center of buoyancy around the center of mass. So same thing applies here. You got center of mass here. You're applying a force from that hand. Where is that force, that line of that force that you're applying relative to the center of mass? Out here, right? So imagine a rowboat with one oar, okay? You pull wide, what tends to happen? Go around in circles, right? Same kind of thing. You start doing too much of this, you're gonna end up doing this kind of stuff, getting this whole snake thing going, okay? Sometimes you'll get that, slight variations of this. It's also a weaker position. If you get out here, you're not actually able to have everything align more properly and use the bigger muscles of the upper trunk to exert that force. So having it more, just inside the shoulder to midline, kind of in that, that classical area, there is kind of a reason for that. We do want to try to minimize this action-reaction that you get here, because that snaking motion that you will see, obviously, is a real problem, because it causes a lot of extra force on the body. Okay, I'm running out of time, so I'm going to skip through some of this. So this was just kind of going through the 4 strokes. Same kind of thing. That footage there. Again, just looking at body position, nice and still, nice stable head, keeping everything moving, nice clean rotation around that one axis. And then, so this is the backstroke corollary really of the freestyle, same kind of a thing. If you can do that kind of a catch and backstroke, that's fantastic, but do watch it, because you will put a big stretch through that anterior part of the shoulder. Butterfly as well is another one. And again, butterfly breaststroke really for me is about maintaining that body position and trying to minimize the amount of drag. Those short axis strokes tend to have a bit more drag, just due to the nature of how they are. So trying to, again, keep that velocity as consistent as possible. One of the big things with that is how high you come up on the breath versus when you're not breathing, okay? One thing to watch, especially if you have underwater footage of an athlete, when you're watching them swimming from the side, really, you shouldn't be able to tell if they're gonna breathe or not until just at the very last second, okay? What you see far too often is you'll get kids that swimming along, not breathing, and as soon as they're gonna breathe, they'll do that. So they'll pick up their head right at the bottom of the dolphin up front. So a lot of frontal area reaction to that, hips are gonna tend to drop. So you again get this cascade thing. Whereas if you're doing it properly, swimming along on the breath, it's just gonna be a chin forward. And that's what you kind of will see with a lot of these guys. Chins stay very low. And if you look at it, this isn't the best image, but it kind of got somewhat of the point across. So breathing in a non-breathing stroke for there. You can't really tell in that slide, and then also again, higher elbow positions. That's again quite weaker. That position there really should be towards the back. So you're trying to keep your paddle big and pushing back. Having a big paddle and pushing up on the water doesn't do you anything, just pushes your hips down. So remember, you got to think about what you're using as a paddle, what direction does the force have to be directed, and how are you going to get the body to do that. Breaststroke, same kind of thing. It's all timing. Everybody knows that, hopefully. Again, head positions, keeping that orientation as clean as you can and as consistent as you can. Not a lot of up and down. Usually when you see the big up and down from the head, that's usually a good sign of fatigue. I don't know if you'll actually see this one or not. So this was actually quite a nice little clip if you watch it slow. If you watch his kick, that cuts it off. But it's a very direct, it's much more direct back than what you would think. It is kind of like, where is he? Like that. So it's definitely pushing back on the water. It's not quite as whippy. And because you're having that much higher contribution of the drag component of the force. Problem with the breaststroke kick, obviously, is that it is largely a born skill. It's really hard to change people to get them, because it's so much of it structural. How your hips and your shanks are actually built. If you look at somebody like Liesel, she was actually almost not knock-kneed, but if you look at the angle through her legs, the way she was built was perfect for a breaststroke kick. She was already halfway there, just in how she stands. Tibial torsions, how much twist you actually have through your tibia. Flexibility, adductors, and then the timing. Again, remember, we're looking at trying to minimize that fluctuation from peak to trough in breaststroke, so that's why that timing is always quite critical. And I think now you're pretty much seeing it pretty consistently. The best breaststrokers, the timing that they use is that the main drive from the kick happens just as the arms are hitting out into full extension. Okay? It's not there and then kick. It's much more closely not simultaneous, but it's a bit more tightly timed. Starts, turns are really all about the action-reaction stuff. So you're getting the body into a position where you're going to maximize the force, getting that impulse right so the time is right as well. So I'll just kind of skip through this. So I'm basically out of time myself. So this, just so in case you haven't seen, this is the wet plate analysis that we'll do at AIS, and they do something similar at QAS now as well, where we measure all the forces acting on the block, rear foot, and then horizontal, vertical force. Green is grab force, and we get speed and things from that. So we can get a pretty good idea of what's going on, so we want to get a good big force curve, shorter period of time, so we get a big impulse, which gives us a big change in velocity. And then again, we spend a fair bit of time looking at body positions and how they're directing that force. Same thing with turns. Again, this was always a good one too. What you will often get in kids, and I see this all the time, especially the kids that are in big programs and they're doing quite busy lane circle swimming. Ideally, you want to get into that kind of a position if you're looking from the bottom. So you look at where the force is. As you push off the wall, nice, clean, right through the center of mass is going to be about there. So that force is nice and straight, directed down the pool, you're maximizing it. As soon as you start doing circle swimming, what happens is that hip angle opens up, shoulders are back up here, so as they push off, that's how they get the ability to circle swim. And that does actually reduce how much is going down the pool, and then it's a habit that they get, so when they race, they'll start doing it as well. So their turns aren't as effective, and they're wasting time and speed. No problem? Okay. Yeah, cheers.